This lecture is looking at section 5.3 from the book on diagonalization. So here we're going to take a couple of concepts that we've seen in the last couple of lectures, eigenvalues and eigenvectors, as well as similar matrices, and look at how these can work together and make problems easier to solve. And then we'll look at some theory behind it. So we're going to look at this first through a specific problem. So this is a problem that we've seen before, where we are looking at a closed system and looking at changes in population over time. So we have the city and the suburb, and we know how people transition between the city and the suburb, with 15% of the city people going to the suburb every year and 10% of the suburban people going to the city. And we've seen how we can use matrices and matrix vector multiplication to look ahead and see what happens in the next year. So we define the variables for our city and suburb population for each year, and then we can get an equation that says, from year one, we multiply by a matrix and we get what happens the next year. So sorry, from year 0, we multiply by the matrix and see what we can get what happens in year 1. And in general, if we know what the population is in any year, we can get what it is the next year by simply multiplying by that same matrix. So this is a problem that we've seen before. But what if you want to forecast way ahead into the future? Well, you can do it 1 year at a time. So you can take your starting population, multiply it by the matrix once to get in year 1, multiply it by again to get year 2, 3, 4, 5, and so on, and just keep multiplying, doing matrix vector multiplication over and over and over and over again, and you'll eventually get your population in the future. Now, just multiplying by the matrices that many times is the same as raising the matrix to a power of n. Okay, so that's multiplying the matrix together n times. Problem is that is a very expensive computation, especially if you have large matrices. It takes a long time to do that computation. So what we're looking for here is a way to do this faster. And there is a way to do it using eigenvalues and eigenvectors. So we're going to look at the problem and say, what's the population after 5 years? Now, this is a small matrix. It's only 5 years, so it wouldn't be too hard to multiply it out. But there is a better way of doing it. So remember, we looked at similar matrices last time. A similar matrix being a matrix that has this property. A matrix is diagonalizable if it is similar to a diagonal matrix. So if you have A equals some invertible matrix P times a diagonal matrix times the inverse of that P matrix, that is called, then we say that A is diagonalizable, or we say that A is similar to a diagonal matrix. And note we looked at this last time, that if A is similar to a diagonal matrix, then A raised to the n is similar to the matrix D raised to the n. And note when you do D raised to the n for a diagonal matrix, that's very easy to calculate. If D is equal to lambda 1 all the way down to lambda n, sorry, use subscripts for this, lambda 1 down to lambda n with zeros on either side, then what's D to the n? Raising it to the nth power is lambda 1 raised to the n all the way down to lambda n raised to the n. I shouldn't use n, I should use m raised to the m, just use different variables. Taking a number and raising it to a power is a lot easier than taking a full non-diagonal matrix and raising it to a power. We can get this power very easily where a to the n is hard to calculate. But notice how many fewer calculations we have in here. Especially if you have large matrices or your power is very large, if it is diagonalizable, you can raise it to a power much easier. So that leads to theorem 5, the diagonalization theorem. An M by N matrix A is diagonalizable if and only if A has N linearly independent eigenvectors. So we've just seen that you can raise a matrix to a power very easily if it is diagonalizable, because you can work with the diagonal matrix instead of your original matrix. So the question is, when is it diagonalizable? This theorem gives you the answer. It is diagonalizable if and only if the matrix has exactly n linear independent eigenvectors. So in fact, A should be a capital A. If it is diagonal, you get more than this. Not only do you get that it can be done, but once you have the eigenvectors and eigenvalues for your matrix A, you also get your matrix P and your matrix D. So D, the diagonal matrix, what is that? That is the eigenvalues. All the things along the diagonal are the eigenvalues of your matrix A. What about P? P, the columns of P, are your eigenvectors. So as soon as you have your eigenvectors and eigenvalues of A, not only do you know that whether or not it's diagonalizable, but you also get your matrix P and your matrix D. So here's an example. This is the matrix that we had for our problem. So find a diagonal matrix D and an invertible matrix P that shows it's diagonalizable. So first thing, we have to get the eigenvalues of A. So to get D, then we said that D, the diagonal of D, is made up of the eigenvalues. So we need the eigenvalues of A. So what do we need to do for that? Well, remember from last class, we need to get the determinant of 0.85 minus t, 0.15, 0.10, and 0.9 minus t, which is equal to 0.85 minus t times 0.9 minus t minus 0.15 times 0.10, and we set it equal to 0 using the characteristic polynomial. So what does this all equal? Well, when you multiply this all out, you are going to get 0.765 minus 1.75 t plus t squared minus 0.015 equals 0. And simplify it, t squared minus 1.75 t plus 0.75 equals 0. This can be factored, t minus 1, t minus 0.75 equals 0. So this gives me my eigenvalues. My eigenvalues are the solutions to that. So I get my first eigenvalue is equal to 1, and my second eigenvalue is equal to 0.75. There's my two eigenvalues. So this gives me my matrix D. So D is equal to 1, 0, 0, 0.75. As soon as you have your eigenvalues, you have your matrix D. Now, how do we get our matrix P? To get the matrix P, we find the eigenvectors associated to this. So we had that D is equal to 1, 0, 0, 0.75. I'll just note it up there. So to get P, find the vectors. So take them in turn. If lambda equals 1, what do we have? We get negative 0.15, 0.05, 0.10, 0.10, negative 0.1. Oops, that should be 1.5. That's what I'm missing. Okay. You can row reduce this now. You get negative 0.15, 0.100, which, if we simplify it a little bit, we get 1 and 2/300. Okay, so now we can take this and we solve it out. We get x1 plus 2/3 x2 equals 0, and x2 is my free variable. So this gives me x1 is equal to negative 2/3 x2, and oops, sorry, I was missing a negative sign up here. That's what's going on. So it's x1 minus 2/3, and x2 equals x2. So my basis for my eigenspace is negative 2/3 and 1. Okay, so there's my first one. My second eigenvector, 0.75, second eigenvalue. You put that in here, you get here you get 0.10, 0.10, 0.15, 0.15. Do our row reductions, and eventually when you do your row reductions, you're going to get 1100, and then you get a basis is simply the matrix -1, 1, or the vector -1, 1 when you go through it. So this gives you your eigenvector for each eigenvalues. So what's your P? Your P is equal to, now when you create your P, make sure you use the same order as you use for your D. So your first column in D was for the eigenvalue 1. So the eigenvector for eigenvalue 1 is negative 2/3 and 1. In D, your second column was the eigenvalue 0.75. So the second column in P is -1, 1. The basis for the eigenvalue of 0.75. So make sure that you keep them similar, or keep them in the same order. And when you have that, you have that A is equal to P D P inverse. Or in other words, we can rewrite it as A times P is equal to P times D. And you can take this and you can check it, okay? But this gives you an efficient way of finding the diagonal matrix to which your original matrix is similar. So now let's return to the problem that we had. We were asked to find the population after 5 years. And we said, you know, doing the matrix vector multiplication 5 times is inefficient. But what we've just done is we have found a diagonal matrix that is similar to our original matrix. So we need to do A to the 5th times our original population. That's the same as this. P times D to the 5th equals P times P inverse. Well, we just figured out what P was. We can very easily do d to the fifth. P inverse takes a little bit of work, but not as much. So in the end, when we multiply everything out, we get a short and much more efficient way of figuring out the population. So now if we know the starting population, one simple matrix multiplication gives us the population in 5 years. And you can see that if now you're asking for the population after 100 years, it's pretty easy to find it because we can very easily take the power of a diagonal matrix. So, Theorem 5. Let's look at the proof of it. So let's start with just some general statements. Now, Theorem 5, you'll note with Theorem 5, it said an if and only if. So it said that it's diagonalizable if and only if these conditions hold around the matrix, or around the eigenvalues. So let's start. Let's say that we have P, just in general. P is any matrix with columns for this. And D is a diagonal matrix with those entries. So we can give a couple of properties just in general about it. So take any matrix times P. Remember what matrix multiplication is. It's really your matrix A times each column of P in turn. So you can write it like this. So it is really just a series of matrix vector products all stuck together. Also, your matrix P times your diagonal matrix, kind of in the opposite order, and done that for a purpose, that is equal to a number times that vector. So note, when we start to compare these two things, which we're going to do in a minute, note what you're looking at here, these pairs. Okay? And we're going to see, when does this happen? When are these things equal? Okay, so the first step. This is a proof that says if and only if. So, and an if and only if proof, you have to say if the first thing holds, then the second part has to hold. Then you say that if the second part holds, the first part has to hold. Okay, so there's two parts to proving an if and only if statement in mathematics. So the first thing we're going to do is we're going to say the first part. So let's suppose that we have a matrix A is diagonalizable. So it's similar to a diagonal matrix. That means that AP equals PD. Just rewriting the equation a little bit. And from the previous statement, we saw that that means the A times V1, A times V2, and so on. Since we say that we're assuming that they're equal, it has to equal the lambda 1 V1, and so on. Well, since that happens, then A1 V1 has to equal lambda 1 V1. And AVN has to equal lambda n Vn, and everything in between. So every column of your matrix AP has to equal the column of PD. So look at what you're getting here. This is essentially the statement of what an eigenvector and an eigenvalue is. We said right off the bat that A is equal to P times D times P inverse, so that means P is invertible. And remember one of the things about invertible matrices. A matrix is invertible if its columns are linearly independent. So P's columns have to be linearly independent. But from our equations up here, it means that they are eigenvalues. So P is a whole bunch of linearly independent eigenvalues of A, or eigenvectors of A. So that's the first part. Now you have to do it the next way. So you have to say that, okay, so we've already shown that if it's diagonalizable, then you have the property with AP being the eigenvectors and eigenvalues. So now take it the other way. So suppose that we have a matrix that has these eigenvectors and eigenvalues. We define a matrix P and a matrix D using those eigenvectors and eigenvalues. Now, is it diagonalizable using these matrices? Yes, it is. So, and note here that this is an n by n matrix. This is going to be important with exactly n eigenvectors. Okay, that's an important point. So, each eigenvalue has a corresponding eigenvector. And when you take these and multiply them out using that stuff we saw at the start, you get AP equals PD, and so it's diagonalizable. Okay. So this proof goes both ways. It says that if you start with something being diagonalizable, that means that your matrix P and D contain the eigenvalues and eigenvectors. Then turn it around and say, okay, if our matrix A has these eigenvectors and eigenvalues with n eigenvalues, or n eigenvectors, linearly independent eigenvectors, you can make the matrix, and that means it's diagonalizable. Okay? So that's the idea behind this proof. Which leads into theorem 6, which uses this and basically says that if you have an n by n matrix with n distinct eigenvalues, then it is automatically diagonalizable. But be a little bit careful. A matrix can be diagonalizable even if it does not have n distinct eigenvalues. So this only works one way. It is possible to come up with a matrix that doesn't have all distinct eigenvalues, n distinct eigenvalues, but it is still diagonalizable. Theorem 7. And now, I've broken this up a little bit more from the book into a couple of different statements. The book puts these all together, so in the book you have a bit of a different perspective on this. I wanted to break out one part of it. So first part, if you have an eigenvalue, then the dimension of the eigenspace is less than or equal to the multiplicity of that eigenvalue. So remember what multiplicity was. If you get the characteristic polynomial, the multiplicity is the power of that eigenvalue in the characteristic polynomial. This statement is actually an important statement when it comes to determining some of the properties of eigenvalues and eigenvectors. The eigenspace that you get has a dimension, and we've seen how to calculate the eigenspace. That dimension can be no more than the multiplicity. So for example, here is a matrix that I've given you, and I give you its characteristic polynomial. When you work out its characteristic polynomial, you will get this. This gives you two eigenvalues. We have lambda equals 6 with multiplicity of 1, and we have lambda equals -2 with the multiplicity of 2. Right away, that's enough to tell you something about the eigenspaces, the size of the eigenspaces. Lambda equals 6, if you work out the eigenspace for that, it is guaranteed to be dimension 1. You're going to get a single vector as its basis. What about the one with lambda equal to -2? Well, what the theorem says is that it's at most 2. So you might get one vector, or you might get two vectors. You can't tell by looking at it, but you will get no more than 2 vectors in the basis. So this theorem, the first part of theorem 7, tells you the maximum size of an eigenspace associated with an eigenvector. The second part of the theorem says that if you have a matrix that's diagonalizable, or if you have an n by n matrix, it is diagonalizable if and only if both of these conditions hold. That the total number of eigenvalues of A, including multiplicities, so you count it, so if it has multiplicity 3, you count it 3 times, then it's equal to n. So adding up all the multiplicities equals the number of columns in your matrix. That's the first condition. The second condition is that the eigenspace for each of those eigenvalues is exactly equal to the multiplicity. So, for instance, in the last thing, we saw that something has a multiplicity of 2. For A to be diagonalizable, it would have the eigenspace for that eigenvalue would have to be exactly 2. And it has to be that way for all of the eigenvalues. So this is a theorem that's telling us when you can have a diagonal matrix, or when you are similar to a diagonal matrix. Let's look at a couple of examples. So this is the matrix that I just showed you a minute ago with its characteristic polynomial. So is it diagonalizable? And if so, find the diagonal matrix and the matrix P that makes it that shows it diagonal. So from this equation, we have lambda 1 is equal to 6 with multiplicity 1. And the second eigenvalue is -2 with multiplicity 2. So what's the first condition? The first condition says that when you add up all the multiplicities, it has to equal the number of columns in the matrix. So you add those up, you get 1 plus 2 equals 3. So the first condition is satisfied. Okay? But it says that both things have to happen. Now we have to look for the eigenspaces and figure out what the eigenspace of each is. So take them in turn. Lambda equals 6. Now, there's one thing. If the multiplicity is 1, you are guaranteed that the dimension of the eigenspace is equal to 1. But this question actually asks us to find it, so let's find it. So if lambda equals 6, what do you get? You take your matrix A minus 6 times the identity. You are going to get 0, -8, 8 going down. You get -4, -4, -4. And down the last one, you get -4, 4, -12. So there's the matrix of A minus 6 times I. Without going through all of the calculations, you are going to come out with that matrix when you reduce it. When you figure everything out, you end up with a basis of that. There is your basis for lambda equals 6. And notice it's dimension 1, exactly as predicted by the theorem. What about the second one? Well, our second is lambda equals -2. Our matrix becomes 8 minus 4 minus 4, and so on. That's the matrix you get when you take A minus or plus 2 times I. Row reduce, go through all the steps, you are going to end up with this matrix. So you can see from this matrix, you have one pivot point. So that means the null space is going to be dimension 2. So right away, this is telling you that the basis is going to have 2 elements. In fact, when you work it out, the vectors that make up the basis will be this. That's the vectors that make up the basis. So that means it is diagonalizable. Your first eigenvector has multiplicity 1. Its eigenspace has dimension 1. Your second eigenvector has multiplicity 2. Its eigenspace has dimension 2. You are diagonalizable. So this shows it is diagonalizable. Now, moreover, at this point, we can get our matrix D, which is 6, 0, 0, 0, minus 2, 0, and 0, 0, minus 2. The minus 2 has multiplicity 2, so it appears twice. Our matrix P, the columns of P now are the basis elements of our eigenspaces. So the eigenspace for the first eigenvector had a basis of a single vector of 0, minus 1, 1. Our second eigenspace had multiplicity 2. The basis had dimension 2. So the next two columns are those matrix elements, or those vectors. Doesn't matter what order you put them in. Okay? But here is your D and your P. So the theorem says that they are diagonalizable, and it also gives us our matrices. Now here's another one, another example. So we have this matrix, and if you work out its characteristic polynomial, you would get this. So is it diagonalizable? Well, take a look at this. The first one, you get lambda equals 1. That's fine. What about the second one? Well, for this second one, notice that there is no real solution. So, no real solution. You have only one eigenvalue for it, so that means it is not diagonalizable. Okay? So, for something to be diagonalizable, it has to meet those two conditions. It has to have enough eigenvectors, counting for the multiplicity, to add up to the number of columns in your matrix. And then your eigenspaces, the dimensions of your eigenspaces, has to match the multiplicity for every eigenvalue. Okay, so what's the summary from this lecture? Diagonal, we have talked before about similar matrices and similar matrices having a lot of similar properties. One of those properties being the eigenvalues are the same. In this lecture, we saw when we can get something that's similar to a diagonal matrix. Why is that important? Because diagonal matrices are very easy to work with, whereas fully populated matrices are difficult to work with. So if you can find a matrix, if you need to use a matrix and you can find that it's similar to a diagonal matrix, sometimes that diagonal matrix will give you some answers much easier than working with your original matrix. This lecture talks about when you can find that diagonal matrix and how to find it, and it's all tied back to your eigenvalues and eigenvectors.